I should have a higher pitch or a lower pitch. It's okay? All right. Okay, let's go into business. So you have seen the title and you were wondering what is it about, and if you don't know Italian, you have seen already what it is about living dangerous, like having electricity power breaking down right before your talk, right? So that's life, yeah? So you know this famous sentence in Italian, it means living dangerously or living on the edge in English. All right, so I will tell you about a few things that we are working on. Some of parts of this talk will be technical parts of those technical parts. You could just skip because you might not fully understand. But I'll try to explain at least the general idea and the basic things, and so that you get a good feeling of what we are doing and what we are up to. So yeah, Katarina was mentioning, and the previous speakers were saying their life experiences about being a physicist and where do you get to travel and how many kind of crazy things you get to see and different cultures and so on. So in my case, I'm maybe quite very exotic from this point of view. So I presently live in Finland after living before that in, okay, I am also from Romania, but then I lived like 7 years in the United States. I lived in Austria, in Spain, in, I don't know, in Switzerland, in many places, yeah? But my base now is in Finland, and guess what I have been doing last week, just before coming here 2 days ago? Well, cross-country skiing, of course. I mean, there is still snow there. You can do cross-country skiing right in the back of your house, of your apartment. Just go out, put the skis, and on the street, you can just go anywhere that you want. Really, I mean, I'm very serious about it. The other thing that I have been doing 2 days ago was that I've been in a conference also in Finland, also with a lot of young and very brilliant people. And we went to sauna, of course, and then we went to jump in the frozen lake. So from 100 degrees plus sauna to plus 3 degrees or whatever, in a frozen lake. Yeah, you cut a piece because you have to cut the ice. That's the nice thing about it. You cut the ice first, and then there's a hole, and you jump in that. Okay, so these are extreme things that I've been doing, but the most extreme thing is in terms of temperature, is actually that I have been to what people call the cryosauna, which is a sauna at minus 110 degrees Celsius. So you get there naked, and you stay 3 minutes, yeah? And then that's supposed to be very refreshing. And it is. If it feels good to be alive after that. Okay, I'm telling you about saunas and cryosaunas because most of the things that we are doing are actually at very, very low temperatures. So we cool things down to temperatures of about 10 millikelvin. That's a very, very low temperature, yeah? So we are getting closer and closer to the absolute value of 0 Kelvin, which you know that thermodynamics tells you that you should not be doing that it's something that you cannot reach in a reasonable lifetime. But we are experts in cooling things to very low temperatures, and in fact, in our lab, in another group, the lowest temperature that has been achieved so far is 500 picokelvin, which is the lowest temperature ever achieved in this universe, unless there is some other group in some other galaxy or multiverse doing similar things as us. But otherwise, we have the world record in the lowest temperatures. All right, so what I will tell you about is a few things about the quantum world. So what do we expect to see in the quantum world, and why is that so different from the classical world, that we are living to? And most of the things that I will talk about relate to an experiment that we did recently. And this is about driving things faster than they should be actually driven, according to what you learn in elementary quantum physics. Okay, so let's see what happens in that situation. But before we get into that, let me tell you why is this important and what are we aiming at in the long run, in general, what is the general picture of our research. So what we want to do is what people call quantum simulation, which is an old idea pioneered by Richard Feynman. So he said the following things that, well, you know, the universe is quantum mechanical, and we don't know how to simulate it on a classical computer. We know that we want to simulate it. We have classical computers, and we know that it's hard to simulate these things on a classical computer. And why is it hard? Because if you look at a qubit that has some Hilbert space, dimension 2, and you have many qubits, then the dimension of this thing, if you have 50 qubits, the dimension of the Hilbert space is 2 to the 50 power, and that very fast exceeds anything that you can imagine that you can do with even a super computer nowadays, yeah? So you just simply have more of these systems that we call qubits, and we very fast exceed the power of the classical computers. So the idea is to use a system, which we call a simulator, to mimic the behavior of another system which we want to understand. And the simulator is something that we can make ourselves, and we hope that we can control it. We hope that we have tools and buttons in the outside lab that we can control the system, which, as we'll see, happens at a very low temperature. We can control this simulator. Now, you might have heard that companies like IBM, Google, Intel, Microsoft, and many others, Rigetti, and so on, there are some startups, they are in a race of making a quantum computer nowadays, yeah? How many of you have heard this in the news? Okay, pretty fair amount of people, yeah. So this is all the time going in the news, like now there's yet another step towards making a quantum, yet another step, and so on. And indeed there is progress all the time, but the reality is that what we have now are rather imperfect systems. So the element of the quantum computer, which is called the quantum bit, is a system that has two states. Yeah, it can be whatever, an atom that has two states. Yeah, you know that atoms have several states. And if you have several of these, you can think about as a register, as a memory similar to your computer, and you put there some kind of information. And then by doing some operations, exactly like in a classical computer, you would expect that you do some thing which is useful. Run an algorithm, for instance. And there are known examples, theoretically known examples of algorithms, such as Shor's algorithm or Grover's algorithm, where you can show that by running things quantum mechanically, you can get a much faster computational power than by doing it with a classical computer. And this, of course, attracts the interest of people working with computers, and attracts the interest of people working with security, because if you have a quantum computer, you can break codes that are used for cryptography, which are based on factorizing numbers. And we know that we cannot factorize large numbers on a classical computer. Therefore, we expect that on a quantum computer, this task will be much easier to achieve. And therefore, if you have a quantum computer, you can have access to all the accounts in the world of people, yeah, and you can get their money or do whatever you want, hack their emails, or I don't know what you want to do, but you can break all the security codes in this world, yeah? And that's very dangerous, of course, and that's why all kinds of agencies, FBI, CIA, NSA, whatever you want to say, they are interested in these kind of things, yeah? But now the thing is that what we have so far are rather imperfect devices, so we don't know how to make something which exceeds the power of a classical computer with these devices. Therefore, we are thinking what we can do with what we have. And this is what this brilliant theorist, whose name is Seth Lloyd, is shown here near a dilution refrigerator, which is a very dangerous thing to put a theorist near an experimental apparatus. You know that? Yeah, there's a famous legend of Wolfgang Pauli going around in Europe and breaking all the machines. You have seen what happened now today here. And so I wouldn't recommend that he stays near your machine if you are an experimental physicist. But he says something interesting, that he says that if life doses you quantum lemons, let's make quantum lemonade. That means that if you don't have something which is perfect, maybe you should not wait for getting something which is perfect. You should do something with what you have, yeah? And that's our ideology now. So that's what we think that we should be doing. We have qubits, which are, in our case, superconducting qubits. Other people have other type of qubits. And so we want to see what is feasible and doable with what we have so far. All right. how does it look in terms of math, this whole thing? So in quantum computing, there are certain criteria which go by the name of a physicist called David DiVincenzo. They are called DiVincenzo criteria. So in order to make a quantum computer, you need the thing which is called the qubit, right? And that qubit should be such a system that you are able to initialize it very precisely. So to put it in the state 0 or 1 or some superposition of it with a very good precision. Then you should be able to manipulate it, to do some operations with it. Otherwise, what is it good for? You should be able to write something on it. You should be able to perform a knot, for instance, on it. If you have many qubits, you should be able to make 2-qubit operations. So things which are conditional on the state of 1 qubit. Yeah, so these are called CNOT gates in the language of quantum computing. But if you have had any interest in how classical computers work, these are analogous to AND gates or to OR gates or XOR gates that you know from classical computers. Yeah? And then you should be able to do the readout of this qubit, so you should be able to measure these systems with a high enough precision, and then, yeah, use this to extract some information that you put there and that you process during the running of the algorithm. Now, in quantum simulation, it's a bit different. You don't necessarily impose all these criteria, and there's, by the way, an important thing which is called the threshold theorem, which tells you that in order to have a universal quantum computer, you need to have these qubits good enough with a precision that is better than a certain number for all these operations that I'm telling you about. Now, in quantum simulation, the idea is the following. You have a Hamiltonian. How many people do you know what is a Hamiltonian? Or have heard? Good, okay. So the Hamiltonian is something which is like the energy for the system. It describes how energy is transformed between, let's say, momentum and position. So if you have an oscillator, the Hamiltonian will be p squared plus x squared with something which depends on the masses. But it essentially counts the total energy of the system, and it describes how it's transferred from one degree of freedom to another, versus from position to momentum. Okay, and then the idea in the simulation is that you have this Hamiltonian, and then you want to do a time evolution, and you expand this Hamiltonian in this kind of power. And then you break it down into several of these Hamiltonians, and each of these Hamiltonians can be run on your computer. And the result of this is that this huge time evolution, which is very difficult in general to simulate, you would be breaking it down into several pieces that are easier to simulate. That's the general idea behind simulation with the digital quantum computer. But more general is that you have a system that, as I said in the beginning, has some degrees of freedom, and you cannot control those, and you want to understand the system, and then you create another system, which is the simulator, that has other degrees of freedom, but those you can control externally. And if the math is the same in both of the systems, then by running the system that you can control, you can understand the one that you cannot control. All right, so what is behind me here, you recognize me, of course, is a reconstruction of a machine that was invented by Charles Babbage, and it's called the differential engine number 2 in technical terms, whatever that means. Babbage was thinking about ways to calculate tables, which were very useful in astronomy, and the way in which they were calculating these tables is by using a method invented by Newton on calculating polynomials, the value of polynomials. And he invented this kind of machine. The machine has an interesting story. So Babbage got a grant from the British government in 1823, so that was quite a long time ago. He got 1,700 pounds to make a computer at that time, to make this kind of machine. Wasn't that amazing? Well, 9 years after that, he makes some kind of prototype that's kind of working. I mean, the principle was there. And he says that, okay, it's good enough. And he got a grant extension from the British government for yet another 10 years to make something really useful. But he kind of lost interest, and he also got in some fights with some of his engineers there, and things at the end of almost 20 years of research, the British government decided that it's not worth to find this type of research, and they cut his grant, and that's the end of the story. Until people, of course, realized in the 20th century, especially around the Second World War, with the work of Alan Turing, how useful computers could be, yeah? And then you know the story since then, how it came. Now, this is really an amazing machine in the sense that it's a machine which is a combination of analytical gears and wheels and levers and stuff like that, and also some digital parts. So it's pretty much like we have now in the lab. You will see machines that are pretty much of this size or even bigger, and the kind of thing that we are thinking about are combining analytical analytical and digital or continuous and digital, if I may say, operation in these machines. Okay, so things look like this. We want to create chips that have this kind of structure. So there are, what you see here is a silicon chip, and on this chip we evaporate lines which are made of metal. It's aluminum, what you see here. This is not a real chip, it's a digital rendering of how we would like the chip to look like, so cool. And they are controlled by external electronics. So these are some things which we call resonators. So they are really pieces, small pieces of metal where the electromagnetic field behaves like really the waves, acoustic wave in this room. So there are oscillations, there are stationary waves that are formed in these pieces of metal. And those things here are the qubits, we call them transmons. And these qubits are essentially artificial atoms. So they are made of something which are called Josephson junctions. I prepared the crash course in Josephson junctions, but the real crash that occurred here probably will not leave me enough time to tell you more in details about those. But they are artificial atoms, if you can imagine this. So we do have the possibility of going in the lab and making something which is an electrical circuit at the bottom, but it behaves effectively like an atom with energy levels. It can absorb energy from outside. Instead, the real atoms that you see here typically absorbed in the optical spectrum, let's say, or X-rays. But these guys, they absorb in the microwave spectrum. That is the same thing. Yeah, it's light in the microwave spectrum. And we can control these things. We can design these atoms as we want, almost with some constraints, of course, but roughly we have a lot of control over them. And we can also irradiate them with all kinds of stuff and control their quantum state. So we can put them in superpositions, 0 plus 1, yeah? Like the Schrödinger cat. This is one Schrödinger cat of a size of about 1 micrometer or even larger. Yeah? So it's a quite sizable Schrödinger cat, I would say. And how do we do them? So we have something which is called a clean room. These are the rooms where your electronics in your laptop or in your mobile phone are made. So there are these people who are wearing masks there because the environment has to be extremely clean. And they go there, and we have this wonderful machine. We sit here and we try to control them. And what we can do is to create this type of structures with a precision of a few tenths of nanometers. That's what we need, yeah? So we can manipulate these metals, these small pieces of metals, with a precision of the order of nanometers. All right, so your task as a future PhD student, which I am sure all of you will be, is to sit here and try to learn all this stuff and try to understand how you can make this thing work for the better of quantum computing, yeah? In reality, they look like this. So this is one sample which is here. It's looked under an optical microscope, and I played a bit with the colors, of course, so that it looks more cool. But you see this transmon is here, this qubit is here, and then there are these wiggling lines that are the resonators. So this is the artificial atom here, and then it's connected by this what we call a coplanar waveguide resonator, which is used for readout in this case. And then we install them in this kind of little boxes. So one of these boxes that you see here is about this much, this size. And what you see here is our connectors, our SMA connectors, which are used to input microwaves on these lines that you see here. These microwaves are traveling through from the outer world in these lines on the chip, entering on the chip here and controlling the transmon, the artificial atom here. And this box gets put in a dilution refrigerator, which is this machine here. It's this picture is taken from bottom up. We put it here, and then we cool it to 10 millikelvin, right? So, and there's another, of course, thing how to cool these machines down, so another skill. And then we have to program all the devices that are used to produce these microwaves and to produce the pulses that are going in the qubit in a certain way. Yeah? So these are instruments that create pulses with a certain shape in the microwave range. Okay, to give you an idea about the price, one of these things is about $500,000. Even one of these things is about 100,000 euros and stuff like that. So things are not very cheap. You will not be able to buy these things and play at home with them for the time being. Please come to our lab if you are interested. All right, so let me say just a few things about the Josephson junctions, which are the key element in what we are doing. So what is a Josephson junction and how does it work? I will just, don't want to get into too many details, just to give you the impression or the idea that things are easy enough that you can understand them with some reasonable effort if you want to put your mind to it. So suppose you have atoms and you put them in this kind of potential, which is a 2L potential, yeah? You can imagine this kind of potential as being anything that you want, but you create a potential like this, like you drop atoms in the gravitational field that has this kind of particular shape, and they are here or here. But they also can tunnel, yeah? Quantum physics allows you for things to tunnel, right? If I'm standing here, I could tunnel through this table on the other side of the stage in principle, but I'm not such a quantum object. So I cannot do it. I'm still a big classical thing. But these kind of guys, they can do it. They can tunnel through this barrier from one side to another. And then this Hamiltonian, which is the magic word that I told you about, can be written in this form. So it has something which is called annihilation and creation operators. So these A and B's are some things that we call operators. And they take particles from one place and they put them in another place with a certain probability T. And then the funny thing is that if you do this calculation, you can write the final form of the Hamiltonian like this. So it has this n squared term and the phi term. And this Hamiltonian is similar to what you would write for a pendulum. If you have a pendulum moving here, and theta is the angle of displacement with respect to the vertical, then this is everything that you need to write to describe the motion of the pendulum. Of course, after this Hamiltonian, you write down some equations of motion for the phase phi and for this n. But for a pendulum, this will look like p squared divided by 2m, so momentum of the particle moving, and then the potential energy, which will be something with cosine of theta, because your particle is displaced by an angle theta or phi, whatever you call it there, from the vertical, yeah? So it's displaced by an angle from the vertical, and it has a momentum p, and it moves like this. And that object, which is called the Hamiltonian, counts the total energy, the kinetic energy of the moving object and the potential energy in the gravitational field, which will depend on the displacement of the object with respect to the vertical. So interesting that the physics of these atoms in a double wave potential is identical, in fact, with the physics of a pendulum. And if you have seen a pendulum and you know how to solve it, then you are able to do quantum computing, yeah? You are already an expert in designing superconducting qubits, and you can come and work with the likes of IBM and Intel and Microsoft and Google. So please go back and solve the pendulum equations. That's my message. Then you know everything. Okay, in reality, how does it look like, and why is it like a pendulum? Because it is in fact like an LC circuit. So what we have here is a junction. This is the reality. It's a close-up in a scanning electron microscope. You see the scale here. This line is 1 micrometer. And what you have here are 2 overlapping pieces of metal. It's pretty much that's it. So it's this one here. These are extra things that don't matter, these side ones. There are some side effects from the fab. But it's this one which has some kind of insulator, and this one, yeah? And so the electrical circuit representation of this junction looks like this, like a crossing here. And then, because it's a line, there are 2 pieces of metal separated by an insulator, so they form naturally a capacitor, yeah? When you have 2 metals, put them near the other, separated by an insulator, you have a capacitor. And this is the symbol which is here, this capacitor. So this circuit works like this. It's an LC circuit. It really oscillates, so the electrons that are on this capacitor, they go like this around back and forth through this junction. So we have an LC circuit which oscillates at a certain frequency, and the fact that it oscillates at a certain, that it behaves as an oscillator allows us to quantize it. So it will be like an atom. But with, instead of the electrical field potential that you have in an atom, you have this gravitational kind of potential for the Josephson pendulum. But the operation of this qubit is like this. Again, the electrons, which are Cooper pairs in fact, but never mind, the electrons are moving back and forth on the plates of this capacitor, and they are going through this junction in the process. It's pretty much what happens here. So these guys are tunneling back and forth between these 2 wells. All right. Now, if you want to see a bit more things in technicalities, and this is kind of electrical engineering stuff, we know how to describe this thing. There are some equations which are due to Josephson, to Brian Josephson, and the Hamiltonian will look like this in the end. And what we have are these 2 equations telling you that the phase, the change in phase in time, is given by the voltage, and the voltage itself is given by this kind of relation in turn. So we know how to solve these things, and we also know that this phase and the number of particles are quantized things, are operators, so they commute in this way. If you have heard of Heisenberg's uncertainty principle, maybe you know that in quantum mechanics X and P do not commute, they are operators, so position and momentum do not commute, yeah? And that's the basis of obtaining the Heisenberg uncertainty relations. While here, what we have is the phase and the number of particles do not commute. And this leads also to an uncertainty principle, yeah? Cool. Now, I will tell you a few things about what we have been actually doing. And this is a bit partly technical. It's the technical name for this thing is STIRAP, which is the acronym for Stimulated Raman Adiabatic Passage. It's hard to remember, right? It took me some years to give this talk. I have been given this talk many times until I can pronounce this without in a single breath, let's say. Yeah, but this STIRAP is very interesting. So let me try to explain it. Yeah, okay, I have put some slides to tell you how we are actually doing it. So this is our transmon, and it's embedded in a coplanar waveguide resonator. And the whole story looks like this. So we have like a 3-level atom here, which you can address with some microwaves called omega 01 and omega 12. We put this inside the field of this resonator, which makes a stationary wave. And this allows us to measure the state of the transmon. So we can find out how many particles or what is the population on state 0, on state 1, on state 2. So this is the technical thing. And another technical thing, so I want to scare you a bit, look how complicated this microwave controlled system is. There's a lot of stuff here and the load that goes in the fridge. So it really, for somebody to start in the field, it takes about 2 years to learn all these technical parts, but then they can really run the experiment and they can produce very nice results. Okay, let me tell you what's the physics of this thing. So stirrup is a very interesting way of transferring particles from one place to another, right? And how do we normally do this? Suppose that we have 3 states. This is what we call a lambda system, because these 0, 1, and 2 are organized, or they are, the structure of this is like a lambda, yeah? Like the letter lambda. So we want to transfer population from the state 0 to the state 2. And we don't have direct access from 0 to 2. Let's imagine that it's a forbidden transition. So how do we do it? Well, we can put what we call a pi pulse, which transfers from 0 to 1, and we can stay in the state 1 for some time. And then we can put another pi pulse that transfers from 1 to 2. And then we are in state 2, yeah? It's basically as if I want to go from here to London, yeah, let's say I will take the train from Frascati to Rome, and then the plane from Rome to London, yeah? So I have to do this in a sequential way. I first take the train from Frascati to Rome, stay in Rome in the airport for some time, and then I take the plane from Rome to UK, right? Why am I insisting on this trivial thing? Just to tell you that in quantum physics, you can do it in another way. And that another way is called the stirrup. And the way that it works is like this. Initially, the population is in the state 0, which we call it a ground state. And then what you are doing, you are actually driving a transition between state 1 and 2. So you are putting some microwave here, which would do something here, and nothing here. Then you couple this transition from state 0 to state 1, and then you are operating on both of these transitions. And then at the end, you keep only the transition from 0 to 1 coupled on here, yeah? And surprisingly, at the end of this sequence, you end up with all the population on state 2. So that is really crazy, right? Because it's as if, think about this in terms of planes and trains. It's as if I want to go to London, and I stay here in Frascati for some time. My plane from Fiumicino takes off and goes in the air. I'm still happily staying here. Then my plane lands in London, and I'm just boarding the train here. I'm on the train to Rome. And when I'm arriving in Rome, I'm actually not in Rome, but in London. And that funny thing is that I have not spent at all any time in the airport. What happens in this experiment is actually, if you look at the population on state 1, which is this intermediate state, which is my Fiumicino airport, it's 0 all the time. It's very interesting, yeah? So I can go from one place to another without going through the intermediate places, which seems to break the continuity equation in physics. Yeah, I cannot go from here to there without going through all the places in between. That might be impossible. But still, quantum physics allows us to do this. And we have actually done this experiment. If you want to understand why it is like this, it is because in this experiment we are actually following. How many of you have taken some lectures on matrices in high school? Some people, okay. So this is a matrix. It's a 3x3 matrix. Okay, good. So the Hamiltonian can be written in this form as a 3x3 matrix. It's as simple as that. And then what we do is something which is called diagonalizing the matrix, finding the eigenvalues and the eigenvectors. And then it turns out that one of these eigenvectors is a so-called dark state. It's a state which doesn't couple with anything in the world, and we can control this state. So all the time we are in this dark state, and that explains why we can avoid being in the state number 1. We can avoid being in Fiumicino, because that state is a combination of state 0 and 2 here. which is this one, this dark state, is 0 and 2 with some cosine of theta and sine of theta, which are controlled by our external pulses. So that's quite cool. We have a system which we can control with microwaves, and we can follow what people call this dark state of this Hamiltonian, so we can control the state of the system at any time. The thing that I want to stress here is that in order for this to work, you have to be slow. Yeah. So in Finland, we have a saying which would be translated in English like, slowly does it, so slowly it's good, gives you a good result. If you act slowly, then you are calm and you will be able to achieve your goals. And that seems to be the case. So in quantum physics, there is a theorem called the adiabatic theorem, which was discovered by Max Born, and Born, the same one with the Born rule, yeah? And Vladimir Fock in 1928. And this theorem says that if you change a Hamiltonian slow enough, you are staying all the time in one of its eigenstates. And this is what we are doing. We are staying all the time in this dark state, and we are able to control the system, the state of the system in this dark state. Okay, now I can tell you what are the results. So you see that the probability or the population in the 0 state is decreasing here when you run the experiment from 1, because initially it was in that state, to 0, while the population in the state 2, which is where we want to go, is increasing from 0 to 1 as we run the experiment. So this is time in nanoseconds. So we control the system with a precision of about 1 nanosecond here. Every point here corresponds to about 1 nanosecond. And so you see that we increase the population here, and at the same time the population in state 1, which is this green one, remains almost 0. So we managed to transfer, as I was saying, we managed to transfer from 0 to 2 without going into the state 1. So that's magic. So apparently we are breaking this continuity principle that tells me that in order to be able to go from here to there, I have to go through all the intermediate places. And you may have known, if you have interest in the history of physics, is how debatable was this type of thinking in Newton's mind, for instance, when he wrote Principia Mathematica, that he said that he was worried about the fact that the gravitational, treatment of gravity apparently implied instantaneous action at a distance, yeah? So when you think about gravitation and Newton's equations, you see that there is nothing that prevents an object from being here. If I move an object here to here, apparently this thing transmits somehow instantaneously to the moon. And this is, to Newton's mind, this was incomprehensible, because it means that something, some action moves instantaneously at a distance, and this cannot be true. He thought that this is a flaw of the theory, of his theory, and therefore other people who would be much smarter in the future, and that turns out to be Einstein, would discover what is the true explanation of this. But here we break this principle, so quantum physics seems to be doing something even more strange than we do expect. Okay, and this, what you see here is the response of our cavity to the field, which allows us actually to do this measurement. So it's a technical thing, if you may say so. And we studied this phenomenon in all kinds of ways. So what you see here is this phenomenon is in this rectangle, which is bluish. And what you see here is a simulation in the lower part, and here is the experiment. So what we notice here is that there is this the yellow-white spot formed here, and this is the signature that stirrup works. So this means that we have a high population here, which has been transferred to the second state. This is the second state. And we see this also in both in the theory and in the experiment. So this is the region where stirrup works. And the other region is just exploring the other parameters, which are differences between timing of the pulses. And we show what happens also in that region. But we see how nicely we can control the system, that even this small oscillations that are shown in the theory, that we do see them in the experiment. Okay, not only that, but we can reverse this experiment. We can do it the other way around. So we can start to put things on the state 2 and then try to bring them back by the same stir-up process to the state 0. Yeah, so reversing of this process also works. By the way, this is a cool thing. Have you thought about this, how strange this quantum physics is? Because nobody tells you, and nobody will tell you, by the way, when you go to the university. Listen to me. Nobody will tell you at the university one funny thing. If you take a spin, a two-level system, yeah, which is this is a qubit what we have. If I take an object from this room, which is this microphone, let's say, and I keep it like this, and then I rotate it by 360 degrees, I bring it to the same position. It's the same object, yeah? If I take a two-level system, which is a qubit, and I rotate it 360 degrees, I bring it to minus the same object. There's a minus sign that it picks up from this. And this is strange, right? How can it be that I rotate an object and I don't get back to the same object? I get back to a different object, which has a minus sign in front of it. You might argue that this minus is irrelevant in quantum physics, but that's not totally true. It can be seen that it is not completely irrelevant. Now, why I'm telling you this is that there is another strange thing related to reversibility. If you have a qubit and you send it to the future and you bring it back from the future, you don't get the same qubit. You get the qubit with a sign minus. That is really strange, right? So you might wonder, how do you bring things back and forth from the present to the future? What can be done? Don't worry. But what I'm telling you is that you will not get the same object back. So please do study quantum physics. There are interesting things that are hidden in the formalism, and it's quite amazing when you discover them, and they are not like in the usual textbooks. They will feed you some kind of machinery of mathematical things, but sometimes they miss that interesting things should be pointed out. All right, so this is what we do. So in our circuit, we have this transpond here, we have the resonator, and we have what we call a density matrix, which characterizes the qubit at any moment in time afterwards. Now, the thing is, this works fine, so we are very happy for what we have done. But can we do something better? And how can we do, in what sense we can do something better? Well, I told you that there is this adiabatic theorem that tells you that I should be slow in doing this experiment. But is there something that I could do in order to beat the adiabatic theorem? So something that I could do so that I could still produce this transfer of population, but in a faster way. And this protocol is called superadiabatic stirrup. It has this SAS stirrup acronym. And it works like this. So instead of having a three-level system and acting only with these two couplings here, which are our microwaves, this omega 01 and omega 12. So in order to put just these two pulses, we will add a controlled pulse, which is this red one here, shown here. And this red thing is, what it's doing is it's correcting all the time for non-adiabatic imperfections along the trajectory of the qubit. And that's a cool thing related to it, because if you add the phases of all these pulses that we are putting here in a triangle like this, there is something which is called the gauge invariant phase, which is something that is very related to stuff like maybe you have heard of Aharonov-Bohm effect or stuff like that. So you have three sides like this and particles jumping from one place to another. If you put a magnetic field here, then you can control the jumping on the magnetic field in the case of superconductors. And everything will depend on this phase here, this gauge invariant phase, which is the sum, the algebraic sum of the phases 0, 1, 1, 2, and 2, 0. So we add this in this order, which is shown here, and this phi is 0, 1, 1, 2, 2, 0. They are the phases of these three pulses here. And everything actually depends only on their sum, which is the gauge invariant phase, and not on of these phases individually. This has been shown also with magnetic fields in many experiments. all right, the machinery looks like this now. So again, it's complicated. It has mixers and all kind of generators here. And you see we start from room temperature here. We go to 50 Kelvin, 4 Kelvin, 0.8 Kelvin, and then around 20 millikelvin. So we get to very, very low temperatures in this experiment. So what do we see? We see that in the stir-up case, we are able to put the population only to about 0.8, while if we do this stir-up case, we are able to increase the population to about 0.9 or above it. So stir-up works better, in fact. Now, how do I understand this stir-up? Let me try to give you a good, simple picture. So the adiabatic theorem is like this. You have, yeah, that's good to get some. You have a glass of water, and then in the adiabatic case, you want to be slow. So you are moving this glass of water slowly here in order not to spill the water, right? Now, if I want to do this non-adiabatically, what we'll have is this. There will be water spilled all over. And this is not what we would like to do. Yeah? We would like to have this kind of transfer of particles in a nice, smooth way. What we do in the stir-up case is that we do it fast, but we would do it also with extra control. So it works like this. Yeah? We are not spilling much water now, even if I do it very fast, because I do some extra degree of control, right, that I'm trying to keep the water inside. Okay, now I'll be arrested for destroying the property of Frascati, but I took my precautions here, so I will clean this, don't worry. All right, so what we see here is that what this shows is also in some parameter space, and this is, this side here is experiment, and this side here is theory. You see that they match quite well, so experiment theory, experiment theory. So what we see is that stir-up works only in certain parameter space, so only here where you see this yellowish color. And we see that it can be done in about 45 nanoseconds time of like me moving this glass. But in the case of stir-up, it works even for faster pulses, like that would be in this kind of region. And we can get to something like 15 nanoseconds, which is something which is called the quantum speed limit. So quantum physics is interesting. It brings you also another concept, which is how fast you can change one state to another. And this is called the quantum speed. And it's limited by a value which is set by the uncertainty principle in energy and time. So how fast you can change one state to another in quantum physics state, I mean quantum state, like 0 plus 1, or the ground state to some excited state. How fast you can change the state of a system into another state, it's limited by a principle called the quantum speed limit. It's not infinitely fast, so that's also very interesting. Yeah, you are used from relativity to things like cannot move infinitely fast because there is the speed limit that limits how fast you can move from one place to another. But in quantum physics, there is also this quantum speed limit that limits you how fast you can change from one state to another. All right, so this is us in the lab. It really is like this. Is this dilution refrigerator, which is used to cool things down, and it has pumps and a lot of machinery there. And this, if you look at the IBM web pages, it's pretty much the same machines. By the way, what they have there is made all in Finland. It's an offspring of our lab that makes these dilution fridges. And then we have a control system, which is with devices like that, with computers, where we can put these pulses and control the state of the system at any time. Now I told you that these things are used to simulate things, so now please read this slide. You will not be able to read very much, get very much out of it, but I just want to convince you that there are things which are called spin chains in condensed matter physics, which are are studied in order to understand magnetism, for instance. Yeah, so you put spins in a lattice like this, and then this gives rise to magnetic phenomena. While in our case, we have this thing with three-level system which acts as a simulator of this spin system. So we have an entire correspondence between the quantities that refer to spin chains, such as the XX interaction and the Jalosinski-Mori interaction. And we have lambda S and lambda A coupling. Lambda S and lambda A are Gell-Mann matrices, exactly the same matrices that we have in quantum chromodynamics, which is the theory that deals with quarks and so on. So you see how interesting the physics goes around. You start with things that are condensed matter, quantum computing, blah, whatever, you end up doing the same physics as quantum chromodynamics. So this is the power of the simulation, that you have a system that has the same mathematical structure as a field theory that is used in particle physics. And then we have, I mean, the Hamiltonians are very similar, or there can be a mathematical equivalence between them. And we can define currents, can define the Wilson loop, can define chiralities, because these currents move in a certain way, clockwise or counterclockwise. And we can do time reversal symmetry in this system. So yeah, these are very technical, but it shows you that, yeah, you have a system that you want to study, which is a magnet, and then you can have a simulator that does exactly, that behaves in the same way in the dynamics as the system that you want to study. And this can be shown also. I want to tell you about Italian physicist we are in Italy called Ettore Majorana, you might have heard of. He's very famous for many things, especially for the Majorana particle. But what maybe is not so well known, that he is also the one who has invented what we call today Majorana sphere or Majorana stellar representation. And the physics that I told you about can be mapped on this Majorana sphere, and the simulation looks like this. So these are it's the stellar representation of the stirrup and the SAS-stirrup process. And this is an extract from his paper from 1932, in which he describes how to do this representation. So it's very nice to think that we are using things that he has discovered so long time ago. Okay, and that pretty much brings me to the end of my story. What you see here is an image of our dilution refrigerator. This, by the way, was made by my son, who is of your age, exactly in high school. And you see here a superposition between 0 and 1 that we have been working on a lot with it. And this is the rest of the machine is something that has a lot of lines, micro-X lines, and also these tubes here are used for cooling. So in order to get to 10 millikelvin, you need a lot of stuff to work on. All right, that's pretty much it. Thank you. I'll wait for your questions.